All right, now we'll move on to Chapter 9, Chemical Bonding 1, the covalent bond. And we'll talk about ionic bonds a little too. Okay, first we're going to talk about dot symbols, Lewis dot symbols. And these are symbols that show the element symbol and the valence electrons as dots around the symbol. So our valence electrons are our outer electrons, which are only S's and P's, because D's and F's always go into inner shells. They're in the inner core. So the highest shell number would be our outermost electrons, and those would be our valence electrons. To do these, we draw a dot to represent each valence electron around the element symbol. And you just follow this pattern below. As you draw in your dots, you would draw the first dot. It doesn't actually matter where you start, but you draw one on each side, and then you start doubling them up. So you'd go 1, 2, 3, 4, 5, 6, 7, 8. And you see they line up along the sides. Okay. If we had 8 electrons around an element, we would call that an octet. That will come in later. Oops. Don't know what that was about. We're not going to worry for now. Okay. An octet, octa is 8, so octet would be 8 electrons around an element. Okay, so for hydrogen, you're going to do this yourself. You're going to fill this chart in. You should pause this. I'm about to show all the answers. So this first column, they all have 1 valence electron, so you should have 1 dot on each. The second column has 2 valence electrons, 1 on the side, 1 on the top. Boron, notice I've cut out the middle of the periodic table here. That's because those D elements, they don't have an effect, and actually none of these elements here have D electrons. So it wouldn't matter. So 3 valence electrons, so we would have 3 dots, 4 valence electrons, 4 dots, 5 valence electron, 1, 2, 3, 4, and then 5, 6, 7, and 8. Go ahead and pause, and here are your answers. Looks really bad. That's kind of messy. Your answers are here. I'm going to put that top back on so that you don't see all this other junk there in a moment. Oh, and here, if you put the dot on the opposite side instead of on top, it really doesn't matter where you put the dots as long as you have enough dots and you have the same number of sides with 1 or 2 dots as shown in here. So if your 1 dot side happened to be for chlorine over on the left or the bottom or the top, that's fine. You should have 3 sides with 2 electrons and 1 side with 1 electron. Okay. Alrighty then. So I didn't follow this exact scheme here for the answers there. As long as it looks similar, you know, you're good. All right, moving on. Ionic bonds. Well, I'll tell you in a second. Ionic bonds are formed when an electron is transferred from a metal to a nonmetal. Electrons are not shared. That's very important. They are not shared in ionic bonds. An electron actually is transferred from the metal to the nonmetal in the bond. A covalent bond, the electrons are shared between 2 atoms. And the way we figure out if we have an ionic or covalent bond is by looking at the difference in electronegativity between 2 atoms. So first you need to learn what electronegativity is. It's a measure of how well an atom attracts shared electrons in a covalent bond toward its own nucleus. And we don't worry so much about electronegativities of the noble gases because only these 2 have been known to form bonds. So when we talk about the highest electronegativity, that would be fluorine. As you go to the right and up the periodic table, electronegativity in general increases. There might be a couple exceptions here, like right here there's a decrease. But in general, as you go to the right and as you go up, electronegativity increases. So why do we care about electronegatividity? This is why. If 2 atoms have different electronegativities and the shared electrons are closer to one atom than the other, that's because of this definition. It's how well an atom attracts electrons. Whoa, we don't want to move that A. How well an atom attracts shared electrons in a bond toward its own nucleus. So, if the electrons have slightly different electronegativities, we create a bond dipole. Di means 2, pole means a pole. We have 2 poles in a bond, a positive and a negative. And the sign for this delta right here is a slight positive. The delta right here is a slight negative. And an example of where this happens is HF. H has an electronegativity of, we can look this up right there, it's 2.20. While F has an electronegativity of 3.98. I'm just looking in this chart up here. That means F, with a larger electronegativity, 3.98 is larger than 2.20, can attract in the electrons in the covalent bond much better than hydrogen. That means the electrons in this bond are closer to F. F has a slight negative charge because those two electrons, one from H, one from F, they're closer to F than to H. So F is getting sort of an extra electron closer to it than it would have without the H nearby. So F has a slight negative charge, and this is noted as delta minus. And one of hydrogen's electrons is farther from F than it should be, so hydrogen will have a slight positive charge, noted as a delta plus. So usually this plus and the minus are superscripted. Okay. In general, if the electronegativity is between 0 and 0.4, we say the bond is nonpolar covalent. Between 0.5 and 1.9, we would say that bond is polar covalent, and greater than 2, the bond is ionic. Now these don't always, they're not steadfast numbers. Sometimes 1.8 is an ionic bond. All right, so these are approximate values. You can use these if I give you a question, would this bond be nonpolar covalent, polar covalent, or ionic? It's okay to use these numbers, but you should know sometimes they don't work exact. But for our purposes, we're going to use these numbers. Okay, so problem. Determine if the following substances have nonpolar covalent, polar covalent, or ionic bonds. We're going to have to find the electronegativities of the two different elements, find what the difference is. So aluminum and chlorine. Aluminum, 1.61, oops, chlorine, 3.16. So we do 1.61 minus 3.16, or 3.16 minus 1.61. You take the absolute value of the difference between the two numbers. We do not deal with subscripts. Even though it's AlCl3, that just means there's 3 Cl's, each bonded to an aluminum, and we're checking each of the bonds separately. So aluminum 1.61, Al 3.16, difference is 1.50. 1.50 is between these, so therefore polar covalent. And we want to draw, if the bond is polar covalent, draw the bond dipole. So aluminum is smaller than chlorine, therefore the delta plus is by the aluminum, the delta minus is by the chlorine, and we draw an arrow right through the bond. There would be 3 of these bonds, all the chlorines connected to the aluminum, but we don't need to draw all of them. Actually, on this side, you'd have a little plus show. So it should actually look like this, with this little line on this end. You draw the arrow toward the negative end, and you put a line across the tail of the arrow so that this looks like a plus right here. If you look at this right here, it's a plus. That's because this is the positive end, and over here is the negative end. All right, HBr, do this on your own. Go ahead and pause. I'm going to show up the answers in a minute. You're looking up the value for H, the value for bromine, subtracting them, finding out what the difference is, and seeing if it's in this range, or greater than 2. And then go ahead and draw the bond dipole. So you should pause and do this on your own. Okay, so we need to put the other end on here. I'm just trying to move this arrow over to here. Okay, there we go. So the H has a smaller electronegativity than bromine. We draw the bond dipole through the HBr bond. Bromine is more negative, it's more electronegative. H is less electronegative, so H has a slight positive. Bromine has a slight negative. Let's do the same for Sb. Pause, and answers are going to show. Okay. The difference between these is 2.01. They're ionic. We don't draw the bond dipole. the electron goes from strontium, it transfers from the metal to the nonmetal. So bromine actually takes that electron from strontium. CH4, C is 2.55, H is 2.20, difference is 0.35. This is nonpolar covalent. We don't draw a bond dipole in there. Okay, now this will become more important, this idea of bond dipoles, later on when we talk about polar molecules. So not through the end of this video, but in our next video we're going to learn about polar and nonpolar molecules as opposed to just polar and nonpolar bonds. Okay, Lewis structures. I mentioned this word octet earlier. Lewis structures show where bonds are in a molecule, and they also show these things called lone pairs. This word lone pair is when you have two dots with no bond, two dots not between two atoms. That would be a pair of electrons floating around an atom, not involved in a bond. These are instructions, and it's important. These are just instructions on how to get the right structure. It's not how this actually happens, because we're going to be taking away electrons and putting in bonds. These electrons that we erased, they were never there. This is just a method to get the correct Lewis structure. One of the things is you have to have all your valence electrons in the Lewis structure. Okay, so let's just go through the things. We're going to add the valence electrons. So sulfur, S, let's see, S has 1, 2, 3, 4, 5, 6. You're just basically counting the columns up to and including the element. O also has 6 valence electrons. So 1, 2, 3, 4, 5, 6. We have 1 S and 2 O's. So in SO2, we have 6 plus, we have 2 O's, so 6 plus 2 times 6. We need 18 electrons, so that's step 1. We added them all up. Draw the stick structure, step 2. You put the first atom in the center, and you put the other atoms around it. All right, so here's our stick structure for SO2. These lines represent bonds. Each bond represents 2 electrons. Okay, fill in octets on all atoms for atoms that have less than 4 valence electrons. Well, these both have more than 4. Filling in an octet means, imagine that there's a box, just like you see this box here, around the O. But we don't want that big of a box. Picture a box around the O, and on each side of the box you have to have 2 electrons or a bond. So it would look like this. This neon or argon, see how we have 8 electrons, the octet? If there's a bond on one of the sides, you don't draw in the electrons because the bond is representing the 2 electrons for the octet. Okay, hang on. Here we go. So I'm going to show you the done version of this. Do you see how on each side of every single element I put 2 electrons? These dots are representing electrons, and I don't put the dots on wherever I see a bond. All right. Step 4. Check if the number in step 3 and step 1 match. Well, step 1 we had 18 electrons. Step 3, we got to add up all these electrons. So if you count all these electrons, so all the ones on the outside plus the bonds, you get 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. You have 20 electrons. That is too many. There's too many electrons. We need to do what this says. It says erase 2 electrons from each of 2 atoms connected by a bond and draw another bond between these 2 atoms. So we're going to erase 2 electrons from each of 2 atoms connected by a bond. So I could erase these 2 and these 2, or I could erase these 2 and these 2, or these 2 and these 2. There's lots of choices here. There's lots of correct answers. I'm going to show you just one possible correct answer. Oh wait, that's all I've done so far. So I've erased 4 total electrons, and then I have to draw another bond between those 2 atoms. Draw another bond between those 2 atoms. So I took the electrons away from these 2, so I'm going to put a bond in here right now. And there you go. We're going to check again how many electrons in here, and is it equal to 18? It's 18. If you add them up, you'll see it's 18. It matches. We're done. Now, could the double bond have been over on the other side? Yes, if we had taken away 2 electrons from this O instead. So again, lots of correct answers. Students always ask me, is this okay? Is this okay? If you have a slightly different answer from these, sorry, from this right here, as long as you have a double bond 4 total electrons on that O that has a double bond and only 2 electrons on the S, 6 electrons on the other O, you're good. Okay, for CH4, step 1. Oh, I should have hidden that from you. Okay, sorry. So step 1, we have to add our valence electrons. Carbon has 4 valence electrons. Hydrogen has 1 valence electron, and we have 4 of them, so we have to multiply 1 valence electron times 4, 8 electrons total. So we go on to step 2, which is to draw the stick structure. Carbon goes in the middle. We'll put that in here. There you go. There's the stick structure. Carbon in the middle, the hydrogen's all on the outside. Step 3, add up all your electrons to, oh no, fill in your octets. Okay, this is a little tricky. Fill in octets on all atoms except for atoms that have less than 4 valence electrons. So, any of these atoms here, these all have less than 4 valence electrons. They have 1, 2, or 3 valence electrons. We do not ever fill in octets for these electrons for our set of rules. We don't fill those in. We only fill in octets for carbon to the end of the periodic table. Okay? So we are not going to fill in an octet. So step 3 is already done because we don't fill in octets, and carbon already has an octet. It has a bond on each side, so I don't fill in a lone pair anywhere. By the way, this right here, these 2 electrons, that's a lone pair, this is a lone pair, this is a lone pair, lone pair, lone pair, lone pair. It's a pair of electrons that are alone, not between 2 atoms. All right, step 4, add up the electrons, 2, 4, 6, 8, and it matches what we're supposed to have, so we're good. All right, SF. And if you want to pause and do these all on your own, that is perfectly fine. Hi, guys. Okay, one of my students wanted to say hi. So, hi guys. Okay, so back to class. So SF4, we're going to again add up the valence electrons. Sulfur has how many? 6. And fluoride has how many? 7. Oops. Homework's on the your schedule on Edline. Okay, so you need 34 total electrons. Let's set up our backbone. Sulfur goes in the middle, fluoride's on the outside. Fill in our octets. And you can pause this and do it on your own. There's our pretty octets. Now we're going to check if we match. So if we add these all up, you'll find that there's 32, but we need 34. So we have a problem. We have to put 2 electrons on the central atom. That's what this step right here says. If the number of electrons in step 3 is too small, add electrons as lone pairs to the central atom. So what does that mean? That means we have to put a lone pair on this sulfur, and I'll show you what that looks like. You redraw the original Lewis diagram, and you put that lone pair, you put it so that it's not sticking out from the sulfur. You put it so that both electrons are attached to the sulfur on the diagonals. Okay, SO3, add up your valence electrons. Again, pause and try this on your own, and I'll lead you through it. Stop staring at me, Chris. If we add up our valence electrons, S and O each have 6, and we have 3 oxygens, so we need 24 total. Put our sulfur in the middle and attach the oxygens to the sulfur. Fill in our octets and add them all up. We find that we have 26 total electrons in here, but we're only allowed to have 24. So what do? We have to erase 2 electrons from each of 2 atoms connected by a bond.
Double bond!
So here we go. We've erased 2 electrons from the S and 2 from the O. I couldn't erase them from 2 of the O's because the O's are not connected by a bond. The sulfur is connected to all the O's. So you could have taken off 2 from the S and 2 from any of the O's. Doesn't matter which one. I just chose the one on the right. And now we have to, now we have to put a bond between these 2 atoms from which we just took away the electrons. So here's our final answer. Now, it would be okay if you had a double bond right here as long as one of the lone pairs was missing from here, or if you have a double bond here, as long as you had one lone pair missing. So the double bond could go between the S and any of the O's. Wherever the double bond is, that O should have only 2 lone pairs, and the other 3 O's should have 3 lone pairs. Okay, CO2. Add up your valence electrons. Again, pause if you can do this on your own. C has 4, O has 6. 6 times 2 is 12, plus 4 from the carbon is 16. Set up our stick structure. C goes in the middle. Fill in our octets. Here we go. Octets are filled. Did you have a question? Okay. Okay, now we're going to compare these electrons with 16, and if you add these all up, you should get 20. Too many electrons. We've got 20, too many. We're going to have to go from 20 down to 16, so this time we have to erase 2 pair and draw in a bond. We have to do that twice to get down to 16 electrons. And this is what you get in the end. And again, you could have these 4 electrons, not necessarily, you have to have 2 on top, 2 on the bottom, 2 on the top, 2 on the side, just 4 total on this side, 4 total on this side. Okay, now one of the things about this method is it makes sure that everybody still has an octet, 8 electrons. Let's just check this O. We have 1, 2, 3, 4, 6, 8. Remember, bonds count as 2. The carbon, 2, 4, 6, 8. The oxygen, 2, 4, 6, 8. Everybody keeps its octet, and we have the right number of valence electrons. So the total electrons has to equal your total number of valence electrons. And if you check any of these final answers, you'll find that every atom has an octet of electrons around it. Okay, last one, AlCl3. Add up your valence electrons. And again, pause. You can do this on your own. Bye-bye. We need 24 total electrons. Set up our stick structure. Aluminum goes in the center. Fill in our valence electrons. But a big note here. We don't put in an octet on aluminum because of that rule earlier that said, where did it go? Fill in octets on all atoms except atoms that have less than 4 valence electrons. So notice aluminum has only 3 valence electrons. So it has less than 4. We don't fill in an octet on the aluminum, just everything else. Check our numbers, and if you add up all these electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. There's the 24th. I know I was missing one there. And we match, and we are done. Woohoo! Okay, moving on. Chemical bonding, molecular geometry. This is very important. It's called valence shell electron pair repulsion theory, VSEPR theory. It says that electrons in the bonds and the lone pairs repel each other to create a physical three-dimensional geometry where electrons in bonds and lone pairs are as far apart as possible from each other. This is a table of what the geometries will look like and their names. You need some definitions first. So, lone pair. Shown you lone pairs a lot throughout the video. Pair of electrons not part of a bond. Steric number. This is a very important term that you need to know. It's the number of lone pairs and atoms bonded to the central atom. People often confuse this and think a double bond would count as 2. It doesn't. It counts as just 1. Because it's not how many bonds there are, it's how many atoms are bonded to the central atom, plus the lone pairs only on the central atom, not the total number of lone pairs. Okay, electron geometry is the shape created by the atoms and lone pairs. Molecular geometry is what you see. The lone pairs are still there. They're still repelling the electrons in the bonds. But you just look at the atoms and say, what shape are the atoms themselves making? So here is a chart. Lots of information here. Your steric number are these numbers across the top. How many lone pairs are in the structure are down the side here. Your electron geometry, see this right here, electron geometry, that top row is always the geometry that the electrons will make. And then down here is the geometry that the molecule will be if there are any lone pairs. If there are no lone pairs, then the geometry for the molecule and the electron is the same, and it's this first row. So for those 6 problems that we just did, these are the 6 problems, we did the Lewis structures for them already, we're going to figure out all of this information for each one. So for steric number, number of bonded atoms and lone pairs. So, and if you can do this on your own, just fill it out. Sulfur has 2 bonded atoms, 1 lone pair. So a total steric number of 3. Okay. And there is 1 lone pair on the central atom. So now we're going to look up our geometry. Steric number was 3. And so our electron geometry is just the first row. So steric number 3, this is our geometry for the electrons, right there. And so you draw the picture. Here's our picture. And the name of this is trigonal planar. Now the molecular geometry, we're at steric number 3 with 1 lone pair, so we go to this box right here. And this stick up here, that's not actually an atom sitting at the top, that is a lone pair. So this little oval shape with the 2 dots, that is the orbital representing where the lone pairs are. And if we look at the geometry of the molecule, just where the atoms are, do you see they are forming this bent shape? Okay, I'm showing you the V or the bent shape right there. And the bond angle was given to you in that little chart here. It said it was 118. And we just want the bond angle for the molecule, not for the electron geometry. Okay, CH4, steric number, bonded atoms. 1, 2, 3, 4 atoms are bonded to the carbon. So steric number 4, and there are 0 lone pairs on the carbon. Electron geometry, we just go to our chart. Steric number 4, remember this top row is your steric number. So the electron geometry is tetrahedral, and there were no lone pairs, so our electron and molecular geometry will both be tetrahedral. And here's our bond angle right there. So that gives you all the information. Okay, SF4. Steric number 1, 2, 3, 4 bonded atoms, 1 lone pair on the sulfur. So steric number 5. Remember, it's bonded atoms plus lone pairs on the central atom. Steric number 5 with 1 lone pair. So we look at our chart. Steric number 5. The electron geometry will be trigonal bipyramidal. So here's the top of one pyramid, and if we draw a line from the top to these 3 sides, that's one pyramid with a triangle at the base. The other pyramid is going from the bottom up to that middle plane. So we have 2 pyramids, bipyramidal, and at the base of each pyramid is a triangle, so that's why it's trigonal pyramidal. Now with 1 lone pair, the molecule is going to be seesaw. This is funny, it looks like a man sideways, but it's like a teeter-totter. So there's a person sitting at this dot and a person sitting at this dot. We have to rotate the dot, you have to sort of rotate that around. And then these are the legs holding the teeter-totter on the ground, and then the person goes teeter-totter, teeter-totter. Oh, and we don't worry about bond angles for that. So, okay, I want to see if I can rotate this to show you what a teeter-totter would look like. Okay, here, so I was able to rotate this. So seesaw or teeter-totter, we don't call it teeter-totter, we call it a seesaw. So the person sits here, the other person sits on this side, and this line right here goes up and down and up and down, and here are the 2 legs holding up the seesaw. I'll put that back to the way it was. There we go. Doesn't matter, you can draw your picture in either orientation. Okay, SO3. Now remember, double bonds count as just 1 for counting steric number because it's bonded atoms. So there are 3 atoms bonded to sulfur, no lone pairs on the sulfur, so it's steric number 3, no lone pairs. We've already done that one. No, we haven't. So steric number 3, electron geometry is trigonal planar. No lone pairs, same geometry, and the angle is 120. And again, you can pause, do this on your own. CO2, 2 atoms are bonded to the central atom. There are no lone pairs. So the farthest apart that these 2 areas of electrons could get would be to form a line. If you look in your chart, you'll see this one's linear, and they're both the same. And the angle, what's the bond angle from here to here? You should know for a line, 180. Last one, steric number 1, 2, 3, no lone pairs. Steric number 3 with no lone pairs, we did that right here. Same as SO3. And we are done.